opening plenary session. So come on in and sit down. And I would like to introduce Dr. Jian Fu, the Wind Integration Systems Integration Manager at the Department of Energy and the Wind Technologies Office. Jian, all right.
Right. Good afternoon, everyone. Can you hear me? Loud enough, okay. Yeah, welcome to ESIC technical workshop and the opening plenary session on offshore wind. So Providence is a great place to talk about offshore wind. US first offshore wind farm, the Block Island wind farm, is not too far away, and we're going to have opportunity to see it on Friday. And if you all remember, Block Island was commissioned in 2016. 8 years have passed. And in 2021, US Biden's administration announces 30 gigawatt by 2030 offshore wind deployment goals. So 3.5 years have passed. What have we been doing so far? So now US has the first commercial scale offshore wind project called South Fork, which commissioned earlier this year. And we currently have 4 offshore wind projects under construction. The total capacity is a little more than 5 gigawatts. The pipeline projects has increased by more than 50% compared to years ago. Those look so promising, right? And you heard from Debbie on the challenges. We have offshore wind project cancellation. We have supply chain problem. We have layoffs like GE. We also have this blade failure event during a construction phase of Vineyard Wind. So in this session, we are together to talk about offshore wind promising and challenges. We are honored to have speakers from Europe and US. We have speakers from different stakeholder groups. We have speakers from system operators. We have speakers from a US utility, from a global offshore wind developer, and from a national lab. So this wide range of stakeholders should be able to share their experience and perspective on offshore wind. So without further ado, let me introduce our first speaker, Antje Orths. She is the chief engineer from Energinet and Denmark. Her topic is offshore wind development in Europe. Antje, the floor is yours.
Thank you, Jian. So yeah, microphone works. That's good. So last year in Tucson, I was there also talking about the offshore wind development in Europe, but then I was talking about the plan to have a plan. Now, actually, we did it. So we have this plan. So we published as Community of European TSOs, electricity TSOs, we together published under the roof of NYISO the Offshore Network Development Plan 2024 in January this year. And I will tell you what this is about. First, again, process. Today we see a lot about processes. So this is a collaboration of member states, of the TSOs and the European Commission. The ONDP is again part of the TYNDP, so the 10-year network development plan. That's something in the United States you seem to envy us for that. So this gets a new chapter, actually a new stack of reports which we have produced now. So first is that the member states have to deliver every second year their offshore ambitions, non-binding offshore ambitions for the year 2030, 2040, 2050. Then we TSOs under the roof of NYISO, we take over and show what this would mean in terms of infrastructure to be built. Then the European Commission in this round, they have to come, or they came actually with their guidance for sea base and cost benefit sharing, because they also understood that it cannot be that the coastal countries pay it all. So this has somehow to be shared in Europe. And you can believe me, we have interesting discussions right now. Then it goes back to actually now the member states have to deliver on Christmas Eve the next round of new targets for the next 2030, 40, 50, while we as NSOE, we then apply the guidance from the Commission on the cost sharing and cost benefit per sea basin, and still a lot of methodology discussions ongoing. So the ONDP package, that's actually one report on the pan-European system, and then we have to report for each sea basin. So in Europe, we have 5 sea basins, and we investigated in the regions what are the specificities of each sea basin. So then we have 5 reports. We also published how we did it, so the methodology report, and we also published with whom we talked underway. Actually, we only had 1 year, which is half of the time which we have for a regular 10-year network development plan. We also developed a visualization tool, so you can go on the NSOE homepage, you can play with the numbers and extract whatever information you are interested in per country, per sea basin, per region, generation or transmission or CO2 emissions, whatever you would like to see per time horizon. And of course, here's the link and a code where you can access the tool. So what is the ONDP? That's actually a translation from the member state targets into terms of infrastructure. So what do we need to build? What do we need to buy? Where to install what? Who pays it? What does it cost? Big questions, where we come now closer to some more informed discussions. So the purpose of the Offshore Network Development Plan is to inform the political discussions in Europe. So, and also, how does it look like? Is everything meshed, or do we continue with radial connections? Where are the meshings? So this we try to find with our infrastructure exercise. As this was not in phase with the regular TYNDP, we used the edition from before. So we used the 2022 edition of the 10-year network development plan and mounted the offshore targets on it. And just to show you that it's, where are the differences? So these are the installed capacities in the scenarios of the TYNDP. And you can see the changes in the dark blue area, which is the offshore assumptions from the TYNDP 22 versus the member state targets. So it's slightly higher than it was in the TYNDP 22. And so we also adjusted with a broad thumb the usage of energy. So the investigation in this very first edition, we stopped at the beach, but in the next edition, 2026, we will have the holistic planning across time, space, and sectors. So here are the numbers from the member states, and also including Norway and Great Britain, to say it this year. So today we have 34 gigawatt installed, and then you see for the decades what are the targets summed up. And you also see how much do we have to install between these decades. So actually now we have to install 22 gigawatt each year. This means both generation, but we also as TSOs have to provide the related infrastructure. And one of the findings was that's actually 9 times this, we have to be 9 times as fast as we have been the last decade. So, and now I'm really curious what the member states deliver in this edition. So if they react to this message or not. So 9 times faster than we have been in the last decade. And also to show you what we did, so we used linear optimization, and we know some offshore hybrid projects we know already. Offshore hybrid projects are projects with dual functionality, so they can connect offshores and they can connect markets at the same time. So this we call offshore hybrid projects. That's the light green at the bottom. And then we offered half of the capacity to the optimizer to try and play with the model and find if there's opportunities to connect international offshore hubs. And the dark green is, this is close to the coasts, and it would be economic nonsense to connect them to each other. So these we assumed will definitely be ready, but half of the capacity was given to the optimizer to find opportunities for new offshore hybrid projects. Yes. You can also see that the ambitions of the member states differ depending on which sea basin we talk about. The most highest ambitions are in the northern seas, which is North Sea, Celtic Sea, English Channel, Irish Sea. Then the second most are in the Baltic Sea, that's the yellow, and the further you come to the south, where they have also different terrain, so they really have deep waters, and they also have space for PV, so they are not really focusing on offshore res, but work with photovoltaics, for example. So we have to increase 15-fold by 2050 compared to today. And this is how we did it. Example, northern seas. You remember the colors. So close to the coasts is dark green. So we assume these will be radial. And then we also have the locations of the offshore parks because we needed this to define the length of the cables that are needed. And we also have information on maritime spatial planning. So we are not the only ones wanting to use the seabeds, but there's fishery, military, sand extraction, you name it. And the governments have plans how to use the space. And so we looked in these plans as far as they were available and have to surround some areas. And this, of course, increases the length of the cables. So we try to consider this as well in the investigations. But communication, again, is then on a high level. So you will only see one dot per economic exclusive zone connected to another country. We did not show which parks the model found because that was not the task. We just inform the political debate, and that doesn't matter which park is connected to what. And this would be interference with the market, which is not our task. Here's what we did. Like every linear optimization study, first we have a starting grid, then we provide the candidates. So it was from each offshore spot to the neighbor offshore spots, and even longer if the country found it interesting to go even further than to the next neighbor. And the third picture, then you see we ran the linear optimization. And then in the fourth pictures, the regions discussed. So kind of when the optimizer found 50 megawatt HVDC connections, so nobody would build this. So we summarized several connections in the same direction to a reasonable technical size. And this is then the corridors that were found. And we started in 30, analyzed 2040, and then 40 was starting condition for 50. Although the regulation, so the law says it in the other way, but we thought that would be too artificial. So we start from where we are today and did progressive planning. Results, you see that most installations will be radial. So these are the capacities, how they are connected. Then the light green is still what we know today. They are in the planning. We did not interfere with these project ideas. And the yellow connections is what we found with the planning exercise. So just a tiny bit on top of everything. So also, you just mentioned it, Jian, we have challenges in the supply chain. So this needs to they need to be overcome. And we also, for the first time, looked at environmental aspects. We invited the RGI, so the Renewable Grid Initiative, which is TSOs together with NGOs, to write a chapter in this report informing about environmental aspects. And we were actually hoping to get recipes. What do we have to do to not violate the environment? But the recipes are not there yet. It's a lot about further looking into this topic together, collecting data and take conclusions and be flexible to adjust the planning and the execution along the way, learning from the findings along the way. So what they hinted at is, maritime spatial planning. We have to consider that, and also we have to consider there are fishes and birds breeding in certain periods, and they have flying routes, and so we might wish to not build in certain periods of the year, or protect mammals or also apply nature inclusive designs, where you see two examples on these pictures. So these are the famous tented fish hotels, which they have at the bottom of the sea in their platforms, or also planting seagrass, because seagrass is good for the environment and fishes and oxygen and everything. Here are the results. Again, you see how much is in which sea basin. And this is, we had several technical designs, meaning one assuming we do have a DC breaker, and another one assuming we do not have a DC breaker. And then we had 3 cost levels. What you see here is the most optimistic version. So this is, we do have a DC breaker starting from 2040, and we have the low cost assumptions. These cost assumptions were from the time of the TYNEP 22. It was before inflation, it was before Ukraine war, and things were comparable cheap. So in the meantime, prices have increased by factor 2, sometimes 3. So this might look different under different assumptions. So this is the optimistic view. Yeah, most you see it in the northern seas and also some offshore hybrid connections. These are the red lines in the Baltic Sea. The green lines indicate what we know today or what it will be radial. And remember the bar charts, the major part will be radially connected. But we have to buy this stuff, and industry has to produce this stuff. So we should not forget about radial connections. So politicians are mostly focusing on these offshore hybrid projects as if they would solve everything, but we have not to forget we need all the assets also to connect, simple connect, like we always did with radial connections. Here you can see the 2 variants, left and right. To the left, it's we do have the DC breaker. To the right is we do not have it. So in summary, it was kind of, we will have 3 times more NTC network transmission connections across jurisdictions when you do have it. The prices are kind of the same, but what you get is very different. So either you have 3 times more international connections or you don't. And having international connections, yeah, you know, the advantages. That's about, it comes later. It's about equalizing prices and better integration of offshore S and whatever. Here you see also the kilometers being part of the total kilometers per decade. This is the shopping list. So this was also the first time that we published this kind of information. So before NYISO tended to communicate gigawatts, but you cannot go into a shop and say, I want a gigawatt. But talking about kilometers of line lengths is a bit more illustrative, and also maybe wake up politicians. So it's up to 54,000 kilometers. So 1.5 times around the globe is the route length. But when you have DC, you have 2 poles, so that take it times 2, and then you know at least what the supply chain has to provide. And in red, you see the numbers for the northern seas only. So just to compare, gray and blue is for all Europe, and red is for the northern seas. Then more than 150 units DC offshore converter stations, AC converter stations, depending if you do have DC breakers or not. And then to bottom right, you see picture, think from Hitachi, DC circuit breakers, up to 34 sets. But there we could discuss if we designed very intelligently or not. But this was our first shoot, so to say. Benefits and challenges. Here are the benefits, no secrets. Better integration of RES, equalizing prices, energy security increases, we can help each other. And here the headaches, system risk. So you might remember we have these 3 gigawatt for all Europe dimensioning as a system security limit, but now we talk about 500 gigawatt, not 3, but 500. And if one light, we assume 2 gigawatt, which is the factual standard we expect in Europe. And if one of this is lost, then we might get interesting problems in the system. General challenges is that if we don't collaborate, the entire offshore dreams or visions, ambitions break down. So we really need to collaborate between TSOs, with ministries, across sectors, with all the supply chain to help each other to get there. So one of the big problems is also port availability. So one number I always remember is you need 2 hectares for a 2 gigawatt offshore wind farm. You need 2 hectares, 20 hectares for 2 years port availability. And to get there, you need to prepare a harbor, you need 6 to 8 years to prepare a harbor. And the European harbors are too small. And there are also other industries who would like to have their space. So this really needs some action. Just to name one, time is over. Then the next topic is financing. So who pays for what? How to share the cost. Also not only the coastal countries should pay, but the other countries as well. And of course, the landlocked countries have a different view on that because they work with PV and nobody is paying their PV and their connections. So we have really interesting discussions right now. The Commission ordered a consultant to make a study on this, and you see to the left, to the right examples. You can have different counterfactuals. So how should the counterfactual look like related to the network or related to generation? And then in June, they published their guidance for the TSOs, but it's still a bit fuzzy and we're still discussing questions like you can see to the right. So what actually, which costs to share from the assets, only the hybrid expansion or the radial part as well, which countries to involve. So there the answer for the first edition is it's only the coastal countries, but it will need to change over time when we can prove that also landlocked countries actually receive the offshore energy. I wanted to include another slide because outside NSOE, we Northern Seas TSO, we have a collaboration now, the offshore transmission collaboration. So if you Google for that, you can see also an expert paper from May this year, where we give our views what we need to do, because we know this, we can be faster when smaller groups of TSOs that are affected and have the ministries in the back that we can go the next step and try to find a way how to share the cost. What could help? Is there a methodology? How can we find out? How can we agree? How can we negotiate? And so in this smaller group of TSOs, we work now at the next paper, and in June next year in Hamburg, there will be a high-level summit of the ministries, and we hope to have the next study ready by then. Stop here. Thank you.
Thank you so much, Antje. Let me reintroduce our next speaker, Jason Frasier. He is the Senior Transmission Planning Manager from New York ISO. That's important.
Hi, everyone. Thanks for bearing with me again. My senior VP, Zach Smith, was supposed to be here. He got conflicted out today. So I'm here to present to you again. Different topic this time, though. So what I'd like to talk through is fairly specific in terms of offshore wind and kind of focus on New York State and how we're handling the planning for transmission to accommodate for offshore wind in New York. So agenda-wise, here's what I'm going to cover is just like kind of what's pushing the need itself and creating the need. Where are we in terms of the actual gen side today? And then what are we doing now and in the future for the transmission side? So this is, I mean, if you followed NYISO or New York State, you're probably familiar with this picture, but this is what's actually driving the need for the generation side. And these are the CLCPA or Climate Leadership and Community Protection Act kind of mandates. So in here, there's a mix of both technology specific goals and targets, as well as kind of percent-based goals and targets. So a couple to point out, I mean, obviously the 9,000 megawatts of offshore wind by 2035 is a big one to talk about today. And two other ones that I'd like to put attention to is 70% renewable by 2030 and 100% zero emissions electricity by 2040. So when we do our policy studies and we kind of do capacity expansion modeling to figure out, hey, what can our system look like? Those are hard constraints that we add to the model and can kind of sensitize or do scenarios around that. But then the technology specific targets are kind of set in stone, and that helps us guide ourselves along the way. And really those are targets that can be implemented at the state level. And I'll get more into that in a couple slides. So where are we today? We have 3, what I would call late stage development or operational projects in New York State. The first, Jian mentioned South Fork Wind. So that's operational today, COD earlier this year. And that is connecting to Long Island. That's 132 megawatts, I think 12 turbines. And that is commercial scale. So that one is currently operating today. The other 2 to mention that are under construction right now are Empire Wind 1 and Sunrise Wind. So Empire 1 is connecting or targeted to connect New York City, and Sunrise Wind will connect in Long Island. The map on the right shows both the kind of cable paths for those 3 projects, shows the BOEM lease areas that the projects will be built in, but also shows the other lease areas that are in the Atlantic, kind of towards the New York Bight. So you can see many of those have been leased, but right now do not have projects that are under construction or advanced development. But what about those lease areas? So going forward, one thing I wanted to mention, and I mentioned a little earlier, so the actual entity that is ensuring that these projects get built and procuring for them is NYSERDA. So that's the New York State Energy Research and Development Authority. NYSERDA is a kind of government arm that does research and development, but in this space, one of the most important things they're doing is actually running the solicitations for these projects. So that is, they put an RFP out, bidders or developers will bid into that RFP to meet the very specific needs that are prescribed in that RFP. And then NYSERDA will take a look at those and provide awards or not awards to those offshore wind projects. So the awards that they provide give that financial kind of PPA or what we call an OREC, so Offshore Renewable Energy Certificate, and give an offtake agreement as well. So at that point, your offshore wind generation developer and project then has financial security and an offtake agreement that they can move forward with. Between 2018 and 2023, there have been 4 solicitations. The 3 projects that are kind of included in those solicitations are what I just showed you before. So 1,900 megawatts worth about. I think Gordon mentioned a little earlier today, there's been ups and downs with contracts for offshore wind projects that have been canceled, renegotiated, and things like that. So there's been a lot of projects that have come and gone through those solicitations, but they continue to move forward. So the 5th solicitation actually just closed in September. So last month, there were 25 project proposals from 4 developers. The total capacity was 6,870 megawatts in total. So if you add that to what you see as 1,900 today, we're getting close to the goal for 2035, and awards are expected Q1 2025. So to hit that point that's how the gen side is getting kind of selected and developed in New York State. Some of those projects that you saw have lead lines with those. So the gen developer is also acting as a transmission lead line developer to get to the onshore POI. So to integrate wind in New York State, all proposed, at least today, proposed points for offshore wind are in New York City or Long Island, 2 very energy dense areas with fairly restrictive security criteria for the transmission system. So it's very much insufficient. The transmission system is insufficient today to handle that full 9,000 megawatt goal. So recognizing that, and I guess one other thing to mention on just the demand side, like if it was a pipe and bubble model and I plug it in there, the demand side is 11 gigawatts of load in New York City peak and 5 gigawatts in Long Island. So Long Island, as an example, we're looking at about 3 gigawatts going there on a 5 gigawatt peak. So if the wind's not blowing on your peak and you're below that, most of the time you're actually exporting from Long Island. And the system itself was not actually handled to do that. It was more of an energy importer. So it's very much a switch in what everyone's used to in this area. So I bring that up because on the bottom right-hand side, you can see for our Long Island public policy study that I'll talk about in a minute, we started with, hey, let's look at the system today. Let's add those 3,000 megawatts of offshore wind in, and what do we see? And you can see it, lit up red, right? So under the N-1/-1 security criteria, effectively, you can't export nearly as much offshore wind as we would hope. So those 3 gigawatts that NYSERDA procured are nowhere near as effective as we thought they would be because you can't inject the energy in the system. So what are we going to do about it? So this is where, and I know earlier I said I try not to bore you with process talk, but this one's really cool. So public policy transmission planning process. So this is NYISO's FERC Order 1000 process. And this is, I could safely say, the most successful process in building the much needed transmission in New York that we have. So it enables us to plan, develop, and cost allocate transmission within the state. So Antje talked about cost allocation. That is a very, very prickly topic, but we've been very successful in this area, and everyone's been happy so far. So one thing I do want to mention, it's unique in different kind of models for procuring and picking transmission or other projects is a sponsorship versus a bid-based model. So NYISO uses a sponsorship model. What that is we identify the need, and you can, I'm not going to read what's on the right, step 1 through 4, so you can kind of go with me on this. We identify the need, but we don't take the next step to pre-design a project. So that means if we see Long Island needs 3,000 megawatts of export capability through transmission, we don't go in, pre-design it and say, hey, here's, everyone bid in and tell me how cheap you can do this. So that's kind of how a bid-based model works. What we do is identify the need at a high level, say we need to export 3,000 megawatts of offshore wind, and then we leave it to developers to come up with creative solutions on how to actually do that. So there's a lot of advantages, there's disadvantages with it, but just wanted to make that note because we see a lot of creative solutions. And I think that's one of the major benefits of that type of model. This process itself has produced 2 large projects that are completed now. One's in development and one is in evaluation, and I'll get to those now. So the 2 completed projects, one is Western New York Public Policy Project. What that was aimed at doing was the Niagara hydro plant in Western New York. Many of you know Niagara Falls. There's actually a very old power plant there that was one of the first in the US. That project was actually getting curtailed quite a bit because of some bulk export constraints on the bulk system near it. So to accommodate for that and recognizing it was a need amongst the entire state, project was solicited for, bids were received, and it was selected and got constructed within the last 5 to 8 years. The next one is our AC transmission. That was actually a much bigger project, so about $1.2 billion. And that was some transmission constraints we were seeing in the middle of the New York system. And those constraints were limiting the effective delivery of energy from the upstate area to the downstate area. So that actually just was finished last year, late last year. There's still a couple straggling components that need to be finished, but for all intents and purposes, it's done. One neat observation that I've made on power engineers is that, us at different ISOs, other countries, is we really like to watch our websites for new records. So like if we have like 80% renewable or something, we're always watching like, when is that 81? And we can put a press release out. It's really cool. This one was the one that I really was kind of proud of. So the highest transfer we ever saw before this was something like 2,500 megawatts across New York State. I think it was like a week after this project went in service and went above 3,000. Not too exciting for everyone to see, but when you're one of those guys that's kind of watching the website for this, it was fun times. Okay, so on to that Long Island Public Policy Project. So you'll hear everyone call it a PPTN. So it's a public policy transmission need. March 2021, and the way the process works is the New York PSC declares the need. So we work with our state on that part very much. And once that need is declared, that's when we go into kind of solicitation mode for project proposals. So that need itself was to export 3,000 megawatts of offshore wind off of Long Island to the rest of New York State. We received 19 proposals for that. And once we get those proposals, we go into evaluation mode. Takes about a year to 2 years to go through all that. And of course, a lot of communication with stakeholders to the extent that we can. And it's very much an open, transparent process. But from a metric standpoint, there's a lot of predefined metrics, and there's some metrics that are unique to each PPTN. For this one, there was, cost, operability, performance, expandability, transmission security, cost savings, and emission savings were some primary ones, but certainly many more. And what did we do? We selected project. So in June 2023, the NYISO board, which is the ultimate decider for the project, selected the Propel New York Alternative 5 project solution. And we always say this is the more efficient or cost-effective transmission solution. So that's language that comes from FERC and is kind of the directive for how to pick the solution that is proposed. Here's a map of kind of Western Long Island and where that project connects. Those are certainly not actual routes. I don't think routes are ever that kind of pretty and smooth, but that's what the project is. It's mainly 345 kV cables that are near or at least sometimes directly onto onshore connection points for offshore wind. So this project was effective, cost effective, and efficient in terms of connecting that offshore wind and allowing it to get off Long Island. Capital cost estimates $3.26 billion for this project, and its required in-service date is May of 2030, which is prior to the 9,000 megawatt goal in 2035. So that's good. Okay, so on to our next. So we covered 3 of the PPTNs. This is our 4th one, and this is live right now. So I can say everything that's public so far and can take questions on everything that's public so far, but there's some that I can't. But I can say, so July 2023 is when the New York's Public Service Commission declared this need through order. Once that need comes out, that's when the NYISO again packages up all of the technical information that developers need to actually design the project, releases it, and then there's a solicitation window, and that closes and we get project proposals. So the need itself is at least 4,770 megawatts of incremental offshore wind. That's a little bit of policy math and how they got to that, but I promise it feeds into that whole 9,000 megawatt of offshore wind by 2035 goal. And this has to actually be directly connected to New York City. So any of the boroughs in New York City has to be connected in there, and it has to be an end-to-end project. And what that means is has to provide a location offshore for offshore wind to actually connect to. So it's effectively moving the POI from onshore to offshore and has to connect to the onshore portion and make the necessary upgrades to actually be able to inject that energy into the system. So very much a tall feat, and that all has to be done by January 1st, 2033. So where are we at with this? June 2024, the solicitation window closed. We received 28 project proposals, and I know this presentation will go out, so I actually did link it there. And they're from 4 different developers. I can say that all projects include some form of HVDC technology, which is probably not surprising when you look at the distances between where the offshore wind bites are to Manhattan. And then currently we're doing our technical evaluations and rolling those out slow in the public realm as we go along. Wanted to talk about some unique challenges with this. And I think there's a lot to talk about. Antje covered some really good ones. First is just permitting. So I think Block Island was, it's a great project in the fact that it wanted to take on those permitting challenges early on and try to get a project from start to finish. And I think some learnings happen with that in the US that our developers are knowing. With this project, the problem is we're connecting to literally the most energy dense area in the US, in New York City. So we've hit a lot of other kind of additional permitting challenges. So what we've done actually is the state has gathered what they call an agency working group, and it involves pretty much every agency I can name that's in New York State. to get together and actually talk to developers as a single unit rather than kind of going out one-on-one talking. So that's one way that that's happened, but there is a large number of permits that have to happen on both the onshore and the offshore area. And all those permits have to be reviewed and ensured that they're kind of up to par for what the projects are looking to do. This one's fun is supply chain. So you saw what Antje in Europe they're looking to do, right? And how many circuit miles of HVDC cables needed. Well, in some way, we're all kind of competing with each other on the supply chain because we're all saying, well, we want it earlier and we need more and we need it faster. So what we see is it's not easy for developers to actually procure these within the timelines that we need them. So we've heard a lot on that. And the last point I want to make was just on timing. So I'd say, there's a lot of efforts in our worlds to move to a more proactive transmission planning process. And I would say this is one of New York's kind of first forays into having transmission ready for when generation wants to connect. So what we're seeing is this constant push and pull with the gen side developers and the transmission developers on how the timing's going to work, who's going to take on that risk for if the timing doesn't work out, and then how to just stage things correctly. So that's relatively new for us and certainly something that we're working on a daily basis. So what's next? We have 7,000 megawatts to go by 2035. Obviously have to get that connected in an efficient way. The Long Island Public Policy Project has to be completed by 2030. New York City Public Policy Project by 2033. So those are kind of the concrete ones. And the last point I wanted to make is, our target is 100% zero emissions by 2040. And is that 9 gigawatts by 2035 even enough? So we've run many different scenarios through our different simulation models in kind of calculating what does it take to meet that. And a lot of them do show a much larger amount of offshore wind coming in. So more things that we're keeping in mind as we work through our processes and work with our neighbors as we talk through this. So thank you very much.
Perfect timing, Jason. So now you heard perspectives from from ISOs and from TSO representatives. Now we have a offshore wind developer here. Let's welcome Christian Bjøl. Did I?
Yep.
Okay, perfect. Yeah, Christian is the head of offshore wind development in Regions America, Ørsted. All right, the floor is yours.
Is the microphone working? Yep, sounds like it. All right. I have fewer slides than my two colleagues here, but the good thing is I think my my story here dovetails well with Antje and Jason have just covered. Just get my technology up and running here. Yeah, so good afternoon. My name is Christian Bjøl. I'm head of offshore project development and bids with Ørsted. As you might be able to guess from my name, I actually happen to be Danish, just like Ørsted. But I've actually been living in the US for the last 12 years. So way before I joined Ørsted a little over 4 years ago. I spent my entire career in energy, starting out in Europe, doing onshore wind and solar. I've always loved a good challenge and solving complex problems. So, it wasn't unnatural to me that my first development experiences were in Italy, notably developing some of the first and only wind farms in Tuscany. And then starting up the Swedish market for my then employer, a market where hydro and nuclear have kept prices very low and the grid relatively decarbonized for decades. My love for problem solving and for wind energy was what set me on a mission to join the offshore wind industry after moving to the US. And being based in New York City, obviously the proximity of the projects in the Northeast was attractive as well. Talk a little bit about Ørsted. As I mentioned, I joined Ørsted 4 years ago, in the summer of 2020, in the height of the pandemic, a pandemic which, along with other factors, obviously have had a huge impact on development of this industry in the US and worldwide. For those of you who might be less familiar with Ørsted, let me spend a few words on introducing us. We are the global leader and the US leader in offshore wind, and we're living proof that the energy transition is happening and that it is indeed a choice. We used to be Dong Energy, Danish oil and natural gas. Back in 2007, 93% of Dong Energy's operating profit came from fossil fuels. In 2012, we started a transformation plan to become a sustainable energy company, which included an exit from oil and gas and a name change to us in 2017. And most recently, here in August, we announced the closure of our last coal-fired plant in Esbjerg in Denmark. And 97% of our energy production comes from renewables. At the end of 2023, we had 15.7 gigawatts installed globally of offshore wind. And this year, we're building more than ever before, another 7.6 gigawatts of offshore wind, including, as Jason mentioned, South Fork Wind, which we commissioned in March, Revolution Wind, which will be delivering power to the very state of Rhode Island and Connecticut, and Sunrise Wind, America's first HVDC wind farm. As you can see here, our US footprint covers not only offshore wind, but also onshore wind, solar, and battery storage. Before diving into some of the challenges and promises of offshore wind in the US from a developer perspective, I did just wanted to do a little spoiler and put up a couple of pictures of our Block Island wind farm, which I know many of you will be touring on Friday. The turbine on the left on the jacket foundation is one of the 5 GE Haliade 6 megawatt turbines of that wind farm. And the 2 pictures on the right are from a very recent tour to our South Fork wind farm, New York's first wind farm and the first commercial scale wind farm in the US with, as Jason mentioned, 11 megawatt Siemens Gamesa turbines delivering power into the town of East Hampton in New England, in Long Island, sorry. So yeah, you can look forward to that trip. Hopefully you'll get good weather. It's even for us who sort of work in the industry every day, it's always very exciting to go out there and get up close. So I mentioned earlier that I like a good challenge, but I guess sometimes you gotta be careful what you ask for. There's certainly been enough challenges coming our way in the offshore wind industry in the last few years. But fortunately, I would say the industry has weathered a lot of the storm and implemented the lessons learned, allowing to secure the future development of the industry here in the US. We often talk about the offshore wind industry as a 30-plus-year-old nascent industry. Oxymoron, if there ever was one. But the US offshore wind industry is definitely nascent, and what the first waves of projects have shown is that the challenges are plentiful. Given the topic of this workshop and the audience here today, I think it's fair to spend some time on system integration topics. But offshore wind projects are complex, in many ways, some of the most complex infrastructure projects that I can think of. And there are challenges and opportunities in so many areas. If we start with a focus on system integration, I think the first and most obvious constraint is that we're developing gigawatt-sized projects in some of the most constrained areas of the US grid, notably here in the Northeast, and where the coastal grid is often not sized for interconnecting projects of this magnitude. Reaching the state's ambitious targets on renewables, which in many cases have to come to a significant extent from offshore wind, requires a lot of planning and creativity from a transmission standpoint. Luckily, in recent years, we've seen many initiatives that are pointing in the right direction and that we commend. We, of course, support FERC Order 1920 and its promotion of a discussion of long-term planning and cost allocation and the use of grid-enhancing technologies. But I also do want to highlight some of the transmission planning initiatives in recent years that have created an easier path to bringing online more offshore wind. The SAA in New Jersey, the Long Island PPTN, as Jason just described, the New York City PPTN, and most recently, the GIP or GRIP funding initiatives in New England. Some of the challenges we do face when proposing to build new offshore wind farms relate to the need for coordination between the various agencies involved in the offshore wind development. This, for instance, could be PJM's new requirement to have full site control for the onshore cable route to progress an interconnection request. This becomes very complicated and very onerous when our inland routes at times can stretch dozens of miles to a solid enough POI if the project, for instance, hasn't been awarded a revenue yet by a state, or revenue contract yet by a state. Another example could be here in New England, where the single loss of in-feed limit is 1,200 megawatt, a size that's below what would be the sweet spot for an HVDC project, and thereby doesn't allow us to optimize the project and offer the lowest possible price to ratepayers. Another area where we face some challenges, oftentimes due to the significant both project development and technology development timelines, is on standards we need to comply with, the recognition of new technology, and dealing with the global marketplace, as both Antje and Jason have alluded to. A hot topic for many of my colleagues currently is around NERC Order PRC 029 and how it could have the potential to impact projects whose substations or converter stations have long been designed, ordered, and entered into manufacturing, and where changes in the worst case could cause months or years of delay with very significant economic consequences for the projects. The last example I'll mention on this topic is how we've often faced challenges when working with the ISOs on submitting models for our wind farms, simply because with the planning horizons of our industry, we're often bidding with future technology, and not even the OEMs are always able to support us with the electrical models of these turbines. Now, if we zoom out from the system integration specific topics, I'd like to touch a bit on some of the other areas where offshore wind in the US in particular, but not only, is or has been facing challenges. Not to make it sound like there's only challenges. I think a lot has been done recently by all industry partners to address these challenges and pave the road for continued success. It's no secret, and I think both Debbie, Jason alluded to it, that quite a few awarded US offshore projects have been canceled in recent years, or in some cases rebid into new auctions. This is in large part due to the confluence of primarily two factors: the long timelines in the US between bid and execution, and the rigidity of the initial contractual frameworks offered by the states. Remember that many of the canceled projects were awarded in 2018, 2019, and 2020, before the real impacts of the inflationary events and the supply chain crunch that resulted from the pandemic and the war in Ukraine starting in 2022. In case the link between the war in Ukraine and offshore wind isn't obvious to everyone, remember that it sparked many European governments to step up their energy independence ambitions and increase the pace and targets for offshore wind, which in a market where the competition for turbines, foundations, HVDC, and vessels is global, has just led to cost increases so stark that it was no longer feasible to deliver projects under their initial contracts. One of our biggest focus areas over the last couple of years has been working with our customers on how to develop the contractual framework to avoid such challenges in the future by having notably introduced inflation indexation into the frameworks, in some cases not just tracking CPI, but actually a basket of indices that better track the cost developments of our industry. Other risk-sharing mechanisms have also become standard, notably related to the cost of onshore grid upgrades, which at times can be very challenging to predict. It's our hope that with the latest FERC reform, there'll be more visibility on this, but it's also important, for instance, with initiatives such as Power Up New England that will develop new points of interconnection in both Massachusetts and Connecticut, that developers get a better understanding of what the onshore grid upgrades will be beyond the investment made in the new POIs. And that ideally there's a sharing mechanism with the customers, so the cost above a certain levels are shared between developers and off-takers. What these risk-sharing mechanisms will do for the most recently awarded projects and for proposals currently under consideration, for instance, in NYISO's New York 5 solicitation by the different states, is providing more flexibility to address the long lead time of the projects, and most of all, address any new quote-unquote freak inflationary events like we saw in the recent past. This allows for contract adjustments without the states being confined to their typically very narrow mandates and limited ability to modify contract terms. And it allows us as developers to not have to factor in anything but our common commodities and inflation forecasting, which ultimately reduces the financing premium and the cost to ratepayers. Obviously, the supply chain and its constraints are another hot topic for us. As I mentioned earlier, we're mostly competing in a global market, which makes it that much more constrained and probably that much harder for US projects since other markets have been able to offer more certainty recently. And some major components, for instance, HVDC, we're not only competing with other global offshore wind projects, but also regional transmission owners, especially in Europe, as we saw in Antje's presentation, where many HVDC ties are planned to go in over the next decade. This can lead to very significant lead times for HVDC systems, up to 6 or 7 years, with early commitment payments, which really challenges developers' early spend profiles on the projects before they are de-risked in terms of permitting or other boundary conditions. Furthermore, having 3 vendors on this essential component is challenging. Another area where we in the US primarily have to choose between 3 vendors is on the wind turbine front: Siemens Gamesa, Vestas, and GE. This also means there's significant competition for their capacity each year, and efforts to establish manufacturing their main components in the US have so far proven difficult for a number of reasons. There's currently much debate in the industry on whether to keep pursuing the bigger is better strategy, always striving for a larger nameplate and a wider rotor, allowing to generate more megawatt hours with a smaller footprint, or alternatively, industrialize the current platforms and assume significant cost out. This plays into another of the current bottlenecks in the market: logistics, and in particular vessels. This, again, is especially true for the US, where we are subject to the Jones Act, mandating US vessels and crews picking up components at the ports. Currently, only 1 jackup wind turbine installation vessel that has been built that's Jones Act compliant. That's the Dominion's Charybdis, which can handle the current 14 to 15 megawatt platforms, but not the next gen 18 to 21 megawatt the OEMs are planning. There's therefore a risk of accelerated obsolescence if the vessels cannot keep pace with the turbine technology on tower height, rotor diameter, but also monopile or foundation weight. Mindful of time, I want to make sure to mention the challenge that is the general administrative layer cake, that is the US. We get seabed leases from the federal government, off-take contracts from the states, where we have to manage interconnection with, but then we have to manage interconnections, with single state or regional RTOs. And we are, so to speak, on our own when it comes to bringing our cable onshore for at times many miles to our POI through coastal communities who can be, to put it nicely, ambivalent when it comes to offshore wind, even if in the state that we are actually awarded in. Permitting is a combination of federal, state, and local, with many stakeholders having a say, and no guarantee that just because BOEM, in other words, the federal government, issued us a lease, we will get across the finish line. So I do realize this sounds like a lot of challenges, but didn't necessarily like a good challenge in the industry. At Ørsted, we are pioneers in this industry. We built the first offshore wind farm in Denmark in 1991, and we've had many firsts. For instance, multiple time building the world's largest offshore wind farm. And with our recently awarded Hornsea 4 project in the UK of over 2.6 gigawatts, we're bringing online ever larger projects. And as I mentioned before, we're this year building more than ever before with 7.6 gigawatts of offshore wind, a lot of it right here in the US. With recent contractual improvements across the board in the solicitations, with more coordination and planning on the transmission side, I fully believe that this industry will continue to grow here in the US and work through some of the many challenges mentioned above. And let's not forget that we're responding to a climate crisis. So really, we should all work on overcoming these challenges and getting some steel in the water. Thank you.
Thank you so much, Christian. Thanks for the pretty comprehensive coverage of the challenges we're facing and left with some forward-looking promise. And our next speaker is Xiaodong Liu, a manager of transmission system planning and from Eversource. He's going to share some mitigation stability issues with offshore wind. Hopefully that's another challenge, or you have mitigation strategies with it. We'll see.
The slides. All right, thank you, Chairman. Good afternoon, everyone. My name is Xiaodong Liu. I'm from Eversource. I'm glad to be here. Thanks to previous presenters' excellent overview of offshore development in the US and Europe. Really enjoyed. So I'm going to discuss challenging solutions in terms of stability issues in offshore wind integration. The stability is very, very critical for the reliable operation wind farm and the grid. Losing stability is definitely not acceptable because it may cause widespread outage. For example, in 2019, a stability issue in the offshore wind farm in UK caused a blackout for over 1 million customers. So, in next 15 minutes, I'm going to share with you how to mitigate the stability issues and Eversource experience and observations from project studies. All right, let me start by introducing Eversource experience a little bit. Eversource started offshore wind study back to 20 years ago when Cape Wind was proposed. Eversource, not sure how many people still remember Cape Wind, 450, offshore wind outside on the south side of Cape Cod. So Eversource actually did a system impact study for a project in 2005, including the steady state, the stability, short circle, harmonics, TRV, TOV, cable energization, de-energization, very comprehensive. Unfortunately, the project wasn't able to proceed. 5 years ago, Eversource partnered with Ørsted and proposed many offshore wind projects, New England and New York area. 3 projects are pretty significant. South Fork Wind is the famous one, that the first offshore wind in federal waters has been in operation since earlier this year. And the Sunrise Wind, the first HVDC offshore wind, is under construction. Another project, the Revolution Wind, is also under construction. In addition to the offshore wind project, Eversource has been proactively identify a grid upgrade to enable more offshore wind connections. For example, on the right, you'll find the Cape Cod Solution Project, which to build a 345 kV transmission loop and a substation upgrade. And the phase 1 project to build a 13-mile transmission line has been completed. And the phase 2 project will kick off next year and expect to complete by 2027. Along coast in the middle of Connecticut, Eversource proposed Hansburg Offshore Wind Hub project to enable 2,400 offshore wind interconnection to the POI. This project is also a part of Power Up New England proposal to DOE, supported by multiple states in the Northeast. Eversource was awarded $89 million to cover 40% of cost. Currently, Eversource estimated that over 13 gigawatts offshore wind can be connected to an identified POI in Eversource service territory. All right, let's back to the topic of stability. Stability is very complicated, as you can see from the diagram, RWE definition and classification. There are different forms of stability across a wide range of frequency, time scale, impacted area, electrical and interaction between electrical and non-electrical. So it's very hard to pinpoint the root cause by simply look at the simulated diagram or even recorded data. Unfortunately, offshore wind potentially can have all of it. So, and it is true that many events have been observed around the world. So how to mitigate the stability issue? So the first step to mitigate the stability, you have it studied, have it thoroughly studied and understood.
The planning study is supposed to identify grid upgrade and improved controls to mitigate stability issues. We have tools and models, EMT tool models, the positive sequence tool and models, and frequency domain, models and tools. Unfortunately, none of them is perfect. So no single tool and model can simulate every stability study. So the industry has been very creative, try to develop a hybrid tool, right, to speed up simulation. And somewhere else had been developing a generic model for the long-term planning purpose. And we have to create study procedures, right, to select tools, models, benchmarking them, and define study steps for the study. But they still have gaps. Right? Another thing to keep in mind is that gaps also exist between the planning study and the actual operations. The planning study is based on lots of assumptions with a limited operation scenario. It just can't cover all the operation scenarios. At the same time, keep in mind that although the planning study intend to be conservative, don't make too conservative assumptions. This is one lesson we learned. In one for project, we make over conservative assumption on the load modeling. The load affect the stability, which create stability issues, which are obviously not real in reality, and nobody was able to resolve it in the study. And this modeling issue was discovered at the later phase of project. We have to go back to run study to correct the study result. All right, this slide I want to share with your Eversource experience of grid forming technology to mitigate the stability issue. People have been talking about the grid forming a lot, including the grid forming battery, grid forming turbine, grid forming the STATCOM, HVDC. Grid forming is needed because the network has a lower inertia and have a lower grid strength due to high penetration of renewable energy resources and retirement of synchronous machine. South Fork Wind installed the grid forming STATCOM in order to improve the stability and for the right through performance, because South Fork Wind actually connect to the weak grid. Now, unfortunately, most of offshore wind in the US connected to the weak grid in the East Coast. So the performance of the STATCOM has been validated and approved in the conventional test, the stable body test, stable frequency test, and we compare the result, recorded data with the simulations. So this device works as designed. It works. Ideally, the eSTATCOM would be even better. eSTATCOM is also grid forming STATCOM with supercapacitors. According to vendor, it also have a larger inertia, which is 10 times larger than the same size condenser. It's amazing. On the diagram below, I show you a comparison of grid forming STATCOM, grid following STATCOM, and eSTATCOM. The blue line is grid forming STATCOM. You can see that it mitigates uncontrolled oscillations and meet the performance requirement of 3% damping ratio. And the eSTATCOM, even better, it completely removes the oscillation mode. All right, standard can't be overstated. It's so important because the planning study is based on the planning guide and all kinds of industry standard, including the modeling standard, protection standard, and the performance requirement standard. They already have some standard industry, the PRC 024, EP 2800, and the new PRC 029. This is good, but don't stop here because there's still lots of room to improve. And this standard need to continuously updated to meet the new technology challenges, like modeling, HVDC, right, for the generic model, the no-code model. Another piece of things seems missing from existing standard, which is related to grid forming capability. For example, performance-based inertia definition, FFR, black start capability. I truly believe that when the system have a lower inertia, now it's time to consider and address low inertia and the stability concerns in more systematic way through standard instead of dealing with this in each individual project. Another challenge we have observed in our study and project is the transparency. The limited visibility models has been affecting our project. What happened is the ISO doesn't know too much about the developer black box model, and the developer doesn't know too much details of the grid. In one for the project, ISO discovered the stability issues, which we couldn't reproduce because it's a stability issue in the action due to interaction between the plant and the external device in the grid. So we have to monitor our control parameters, communicate with ISO back and forth many times. ISO tests the one set of parameter and it barely meet performance requirement. Then we told ISO, don't bother me again. I'm all set, Don't call me again. So there's no optimization, and it's very hard to do optimization without the model details. And something like this won't be good for the other project in the queue. So we see that have a lot of room that to enhance the collaboration and the transparency between different parties in order to streamline interconnection process, including achieve coordinated control, optimize the performance, and speed up the study. All right, when offshore wind is energized and put in operation, actions to mitigate stability are normally based on operation procedure, which are predetermined based on comprehensive transformation planning studies. Actions could include the limited operation, generation curtailment, redispatch, network reconfiguration, and dispatch a more dynamic reactive device online if the voltage is related, and turn on AVR for more generators, or apply strict limit to interface flows. We all need a better situation awareness, real-time monitoring alarming. The operator operate the network based on the procedure and alarms. We may also need additional design support tools because the stability assessment is normally not included in the traditional EMS. We may need a real-time stability simulation, PMU applications, online inertia estimation. I'm not sure if somebody dispatch a generator using inertia, but it may be good to have. And some others are exploring more fancy stuff, digital twin, AR. Of course, the good practice equipment maintenance to reduce the equipment failure rate is also good. So all of the effort will contribute to maintain the stability of the system. All right, and now comes the protection. Protection is so important. It's the last line of defense. They already have some protection in the system for the system stability, like generator protection, fungicide protection, and some rust transfer trips, and wide area protection. So what's the difference when you have offshore wind? The difference is when you have a larger scale of your wind, you will have a much larger range of frequency event, which could not be fully covered by existing relays. They have a lot of events that observed around the world has proved that they still have gaps. So you still need to continuously study it and prove the relays. You may need more system-wide protection depending on the study result. Right, then what's next? So we studied, put in operation, have a protection in place. Are we all set? Definitely not. The Murphy's Law tells anything that can go wrong will go wrong. Unexpected always happen. It already happened in the two projects that currently in operation on the Plenary we have in US, right? Made an incident. So I'll give you a couple examples. You know, one incident was caused by human error. One incident was caused by incorrect relay settings, right? One incident caused by power quality issues in the grid, which failed cooling system of plant and tripped the whole plant. Another one was caused by mechanical failure of the turbine, right? Another incident was caused by mechanical failure, another major equipment. Another one even more interesting. A chip in the plant trip a cable in the grid because of the TOV issues. That cable even not connected to the plant. So we still need to brainstorm all the possibilities, develop and test contingency plans, learn and improve from event. Close the loop, improve every piece of the loop, keep improving, and stay optimistic. Very important, stay optimistic. So what I remember is about 20 years ago, many states developed to start to develop the onshore wind. The people were very nervous about 10% onshore wind penetration. Many questions are asked. What about the resource adequacy? What about the market price? What about the balance of supply demand, right? Real time, hourly and intra-hourly. What about power quality, like harmonic issue? What about uncertainty? Many questions. But now, many states have a 20%, 30%, or even 40% wind generation. So I truly believe offshore wind obviously the next big thing for the country. And we can, with full confidence, overcome all the technical challenges and keep light on. That's everything I have today. Thank you very much.
Thank you so much, Xiaodong, for the positive outlook. Now we heard 4 presenters. Our last presenter is going to share some of the activities that federal government is currently working on. So please welcome our next speaker, Travis Douville. He is currently the wind energy grid integration lead from Pacific Northwest National Lab. I just want to add one more thing to introduce you. Travis had worked on detail with Wind Office and supporting the development of Atlantic Offshore Wind Transmission Action Plan, right? Very good. Okay.
Can you hear me? Is it working? Okay, great. All right, well, good afternoon, everyone. Thanks for being here today. Looking forward to telling you about what your government is doing for you when it comes to offshore wind transmission, but also taking you with me on a trip back west, where I'm from. But we'll start here on the Atlantic coast. But we learn as kids here, you know, America the Beautiful, you sing it in school growing up. So one of the lines from sea to shining sea seems appropriate here. Here's what the Department of Energy is doing when it comes to offshore wind transmission on the major coastlines of the United States so far, and there's more to come. They've started on the Atlantic coast. People in this room are probably familiar with that effort. They started with the gaps analysis. I was part of that team, as Jian just mentioned, that did several years of convening. Some of you in the room we may have talked to come up with recommendations to facilitate transmission for this emerging new resource and to fully capture the opportunity. At the same time, there was an Atlantic offshore wind transmission study that was executed by NREL and my lab, the Pacific Northwest National Laboratory, under WIDO, Wind Energy Technology Office funding. 2-year study was done in conjunction with the convening, and both of those efforts resulted in this action plan that I'm going to tell you about in just a moment. So that was the Atlantic Offshore Wind Transmission Action Plan. So the point being, we can study things all day long, but eventually we need to think about steps and mandates and authorities to actually execute on a vision. And a lot of that's outlined in the action plan. Then we've started on the West Coast, where we've done a gaps analysis, also under WIDO funding, and convening and study work that's underway currently under Grid Deployment Office funding. And an action plan will result out of that work as well. The last thing to mention is that the Gulf Coast gaps analysis has begun. So you can kind of see what's coming, right? There's a clear process to the way the Department of Energy is going about understanding the opportunity here. So a little bit about the action plan. There are 41 recommendations. This came out in 2023. There are 5 key categories. You can read those on the slide. Co-drafted by the Department of Energy and BOEM. So BOEM is the federal entity responsible as part of the Department of Interior, responsible for leasing the water for offshore wind development. Most in the room know that, but they were a key partner in developing these recommendations. So I'll give you a few highlights in terms of, sure, there's this beautiful PDF. I mean, there's all kinds of great ideas in there, I think, but you know, we don't want it to be a stale document, and we want it to drive action. So here's a few things that have happened, and it's pretty exciting because I walked away from this for a year at least, and to come back to it and to see what's been done is encouraging. And there are people maybe in this room who are part of this one, the Northeast States Collaborative on Interregional Transmission. This is one of our first recommendations in the plan, and it was exciting to see this adopted by the states very early on. And the list of states has grown, and I even feel like maybe Northeast shouldn't be in the title. You know, and as time goes on, it's certainly centered there, but as time goes on, more states are joining. So you've got states that are part of ISO New England, part of New York ISO, and part of PJM already in this collaborative. And the idea is to bring the states together to provide shared recommendations, align solicitations, eventually organize around cost allocation strategies in a way that a single RTO or ISO can't simply do, and certainly DOE does not have the mandate or authority to do any of that. So we see strong role for the states to help drive this coordination of transmission. What was one of the key findings out of the Atlantic study was how valuable, particularly off the Atlantic seaboard, coordinated transmission could be. Now, how to execute on that, not so simple, but this is a step in the right direction. I'm going to come back to this one in just a sec. There's another one here around this 1.25 million award around standardization. I think every speaker, I was keeping track. I'm pretty sure every one of you mentioned standards at some point. And so here is funding is a call that's out right now on standardizing offshore wind transmission infrastructure, aligning on capacities of export cables, and not just now, but into the future, converters, substations, things like that, and also future proofing. So we think about mesh ready design, some of the things, the very interesting things that have come out of New York State. How do we make investments now that preserve optionality and support the emergence of this industry into the future? Related to that is this funding that's come out of the Wind Energy Technology Office, specifically around HVDC. So standards again, and workforce funding. Both these things were mentioned, I believe, by Christian and others, to try to really pull out here the HVDC interoperability and HVDC protections that are going to be needed to truly unlock offshore grids that some of these studies that I'm participating in are indicating as quite valuable. All right, so now we're going to hop to the West Coast. And so I lead the West Coast Offshore Wind Transmission Study. There's a lot on this slide. I just want to tell you a few things about that study, give you an update. If you have any questions in the Q&A period, I can take those. So we start with capacity expansion modeling, very similar to the Atlantic study, very similar to maybe some of these other, renewable, integration or emergence studies that you've seen in the past. We start with capacity expansion modeling at a zonal level. This time we do nodal builds. So when I say nodal, I'm talking about specific plants, lines at 230 kV and above, typically rating. We do that we split that offshore and onshore, and we build production cost models that have nodal definitions of the full Western interconnection. So that's a 20,000 bus system now built out with offshore wind components that meet up to the zonal capacity expansion targets, which I'll tell you about in just a moment. We look at resource adequacy, and then we step into the power flow domain, and we do reliability and resilience work there. and identify a set of upgrades required across the Western interconnection to achieve full reliability as coordinated with system operators on the West Coast. Finally, we step out and we do techno-economic evaluation, which is going on right now. So the kind of the darker bubbles here are work that's been completed, and we're in the phase now of doing the final touches on the economic analysis, and then we're going to be reporting out. One other mention on this slide is that we have, for the first time that I'm aware of on a transmission study, is this piece called community benefits analysis or community values analysis. So we're trying to consider through some natural capital modeling the impact of siting decisions, and keep in mind that nothing we do is true siting. It's not, this is all, conceptual. It would need to much more detailed spatial planning work. But for what we have now in terms of exclusions and frictions that we model into our routing geospatial analysis, we consider the impact, for better or worse, on various ecosystem services, which have been prioritized by a subgroup assembled around this community values analysis theme. And then we consider the way those ecosystem services may be enhanced or degraded and how that impacts people. And so and ultimately on this study, we're just probing that for the first time. We do think in the future, and some early findings are that would be a very helpful thing to include in the transmission planning loop, but is not standard today. All right, I mentioned capacity expansion. Just two figures for you from this slide. With the assumptions that we have made in the capacity expansion tool, governed by system operators and state planners and folks from industry and environmental NGOs and the whole 220 plus advisory committee, member advisory committee that we have, we end up with 15 gigawatts of offshore wind on the West Coast by 2035 and 33 gigawatts by 2050. So it's not quite as much as you might have out here, but the challenges on the West Coast have to do with the steepness of the continental shelf, the fact that everything has to float, that includes transmission, and the floating depths are extreme. They're much deeper than other places in the world where floating technology has been deployed. So we're going to need to harness the best from our oil and gas industry and harness the best from Europe and the work that's being done around various mooring designs. And but these topology sets that I'm showing here, which can be thought of as scenarios into the future, they all are going to require floating substations, floating platforms with breakers, floating turbines, of course, floating converters in many of them, where HVDC is important. So there's a lot of work to be done in terms of standards and technology development to make all that a reality. We try to model what would be the value of such builds if they could be made, and we try to come up with accurate costing of those systems, which is a challenge today. So we have these 5 that are on the screen here. And I'll just read them quickly. The radial distributed case is a 2035 scenario where we have 15 gigawatt, those 15 gigawatts, 13 of which are in California, 2 gigawatts are in Oregon, distributed among 9 POIs. So think of points of interconnection. Think of the energy spread out when it's coming to shore, maybe a more nuanced, more gentle infusion of that power. And then the radial concentrated case presents an alternative 2035 where we do chunk flows, and we try to minimize the number of places we touch on the coast. We put a lot of power through each one of those points of interconnection. And then in 2050, we have a counterfactual, which is purely radial interconnections. And then we study these coordinated intra-regional and inter-regional cases. I'm not showing the exact topology sets because it makes your head spin a little bit, but suffice to say that we've designed the experiment so that one can go from any 2035 to any 2050, which yields, how many arrows there? 6, I think, different arrows on the screen. So those are 6 different feasible development pathways, and we can assess the economic benefits of doing one versus another. So just a little bit, in terms of give you a little bit of results that we're seeing, and apologies for some of the formatting of the slides. I'm just seeing that now, but a little bit on the resource adequacy findings, which are preliminary, but I can tell you that we use this grid path resource adequacy toolkit. It has 38 zonal, it has a 38 zone topology across the WEC. It captures key path interfaces, line ratings, path limits from the production cost model. I'll let you read the rest. We include forced outages for thermals. We don't weather in a weather-dependent way, derate any other variable generation, for example, or energy storage. And then importantly, hydropower and energy storage dispatch assumes perfect foresight through 7-day subproblems. So every year is broken up in 7-day subproblems, and we dispatch with perfect foresight across those days. And then we put all 5 topology sets through that model. And let me tell you a little bit about what we've emphasized in this model. This model tries to prioritize coincident weather. So we've included, and I'll tell you how in a second, 43 historical weather years. And then we can apply warming to those historical weather sets and look at 2 sets of 40 future weather years, and then run those against historical records of 22 hydropower years. Hydropower on the West Coast is extremely important in terms of power sector dispatch. So we end up with 2,706 simulated years with coincident supply and demand. So how do we do that? We take we borrow from this thermodynamic global warming numerical weather prediction data set, which gives us historical weather from 1980 through 2022. And then we apply warming, as we've done in this integrated multi-sector modeling project, to evaluate a cooler, warmer future and a warmer future, spanning 2020 through 2059. And we pull wind and solar plant configurations from the EIA 8060 database, and we also can augment this with future plants that we're putting in these builds out to 2050, for example. And just a word on that. These are the kinds of things we can do with this data set. So we can look at extreme events in the West. I think a lot of people in the room, I mean, I've read some great ESIG reports about extreme events, and we're certainly hearing from system operators there how concerned they are about heat waves. Heat waves in the West, I don't know if these are an issue here as much, but maybe I need to educate myself. In the West, we have these high pressure zones that settle over large geographic areas. They depress horizontal wind shear gradients, and they drive up loads precisely when they decrease land-based wind fleet production. And so there's a real concern with these events becoming more and more frequent. We do see them somewhat stable, plus or minus 3 days in the historical record. But how are we going to meet these extreme events going forward? Bonneville has asked me that question explicitly, and they will often, pull one event at a time and say, "See, this is why we're so concerned." But we look through the historical record, and we find that these line up in a plus or minus 3 day. We've done the same thing for cold snaps, and these align for the various BAs across the Western interconnection. And then we can consider these are gross capacity factors across all those 43 historical years. Considering the 10th percentile, the 9th percentile, and the mean of production of the fleets installed in the far left column and the balancing authorities of Bonneville Power, several of them added up in NYISO, and then in the bottom row, Pacific Core West. And these are the 3 areas of the grid that we track closely on the West Coast study. And then on the other columns, columns 2 through 5 there on the running from left to right are the offshore wind topology set scenarios that we've run. And what we can see is that, sure, offshore wind has a higher capacity factor than the land-based fleet. That's on average. That's not a surprise. People know that already. But what's interesting is to think about how that resource might be available during these heat waves or not. So you can certainly see if you look at the top row here, how low the production is for Bonneville during a heat wave. This is why they're concerned. It also shows up in Pacific Core West because there's similar wind plants being wheeled to Pac West. But in California, you don't see it as much. It's a little more consistent there. When we look offshore, sure, capacity factors are higher. We still see a drop during the heat wave, but it might be mitigated by such a robust capacity ahead of the heat wave in Bonneville, for example, which allows you to preserve your hydro resource going into that event. But then in California, a similar trend happens in Pacific Core West. But in NYISO, it's relatively flat. So you don't see a big change through the heat wave. So there's some inherent complementarity, some ability to share this resource across these different balancing authorities precisely during these scary resilience extreme events in the West. The story with cold snaps is a bit flipped. It actually appears that California maybe sees more of a drop in production during these cold snaps, it's plus or minus 3-day window, particularly in the day of day 0 of the cold snap, whereas we don't see the same trend in Bonneville and Pacific Core. So there's some interesting sort of anti-correlations here that could be useful if transmission could support the sharing of power across these regions. All right, and then just lastly, before I show you the preliminary adequacy results, we also have a way to train that historical weather through a neural net that allows us to predict loads, conventional loads. I mean, loads as they've been in the historical database through historical weather. And then on this study, we've added this bottom-up energy demand forecast through evolved energy research, which allows us to predict load electrification impact on 2035 and 2050 loads. And we've trained that against all that historical weather. So now we can go from all the historical weather to electrified load data sets, and then we run all that together. The last piece is the hydropower observed monthly and weekly volumes from the EIA 923 database from years 2001 through 2022. I won't spend too much time here. We developed a method to define effective load carrying contribution from this tool in a way that tries to balance all 3 regions. It's a little tricky that the loads in California are dominant on the West Coast. So it's a little bit tricky to make sure you can see kind of a balance point where all 3 regions are seeing a 0.1 LOLE, a loss of load expectancy. So then you can see, well, what's offshore wind giving me around that point in all 3 regions? That's what these steps are describing. And then here are the trends that we see. And maybe unsurprisingly, most of the value that we see is incurred by those California, all of the value we see is incurred by those California net load peaks and August evenings throughout the historical record. So we don't actually attribute just on its surface any resource adequacy value of offshore wind or offshore wind transmission directly to Pacific Core West or the Northwest, which includes Bonneville and Portland General Electric and Seattle City Light, Tacoma Power and Water, Puget Sound Energy. But we do see really high effective load carrying contributions. So on the order of 50% early on in 2035, degrading slightly to 40%, 41% later on in 2050. But still a very, very powerful resource, a very useful resource in terms of capacity. And I'm not suggesting that this is the way this would be remunerated or allocated across the regions, but this is just the inherent complementarity of the resource. But importantly, and a key distinction from the Atlantic work is that the transmission itself does not carry a strong capacity contribution as it does in the Atlantic. All right, that's all the work I have, but look forward to taking